Wow.
Okay. Hello, everybody. Thank you for coming to the DREAM seminar today. Today, we're happy to welcome Dr. Anna Rufino Ferreira. Anna received her PhD in EECS in 2015 from Berkeley under the supervision of Murat Archak. And after that, before this, she was at the University of Porto for a few years as a research engineer working in the area of robotics. After she received her PhD, she was at Apple in the Special Projects Group for a few years, working on autonomous systems. And most recently, she's now been working at Lyft Level 5 on predicting traffic behavior of other agents. So let's all welcome Anna here today.
So today I'll focus on how we are leveraging large-scale data to predict traffic agent behavior, and this is specifically for autonomous driving. So how we are integrating this, how we are planning to integrate this in our autonomy stack. So first I'll give some context about what is exactly the prediction problem and where does it fit in the autonomy stack. Then I'll give an overview of what have been the classical approaches for prediction of traffic agents, and then the recent deep learned approaches by some of our industry competitors, I guess. And then the idea is how can we mix these two approaches and actually make it work in the car and the challenges. And then time permitting, I'll talk about the data sets. How do we actually create a data set for the prediction problem? What are the issues? What are the challenges? And then finally, a little bit of the Lyft Level 5 data set that was released at CPAR this year. All right. So prediction. Let's see if I can make this movie work. So first thing is, so this is happening, coming to an intersection, car is coming here, and now something is happening. Anyone wants to guess what's going to happen? No crash, because we weren't driving autonomously. Okay, a little more. A little more?
It's going to fall.
No. Just what's the behavior of the car? Turning left? Yeah, it's actually a U-turn. And this happens on the road, right? So that's the prediction job, is try to infer what is going to happen in the next, let's say 1, 2, 5, even 10 seconds for the planner to help the planner decide what is the best action that our car, which I will call ego, for our own car that we are controlling. What is the best action that it can do? So a little bit of the stack. So prediction lives here at the intersection between perception and behavior planner. Perception tells us this is all the obstacles on the road. This is the type of obstacle. This is how it's moving. This is the same obstacle. This obstacle we see now is the same one we've seen in the previous time steps and before. And then prediction then tries to infer what are the different behaviors. I'll get into more detail. And then that goes into behavior planner. Okay. All right, I'll stay here. That goes into behavior planner for higher level decision making. Wow. Okay. That's not, okay. The behavior planner figures out, okay, maybe there's a few types of behavior that we can do. Trajectory planner will calculate an optimal trajectory for different behaviors. Then we get decided which one is the best for the goal that we have in mind, where do we want to go. And then that gets fed to controls and the car actuates. So a little bit more in detail. So prediction actually takes roughly 3 inputs. Let me see if I can get that slide out of the way. No, okay. So we get the ego pose, where the car is in the world. We get a lot of map information. I'll give more details about it. And then perception obstacles. And then So this is what we have on the right, information about the map. So maybe this lane is here, you can actually turn right. This is what's encoded here. There's a path, turning right, going straight, turning left. There's a crosswalk in there. And so then when you have a car here, by pink is our ego car. And so there's an obstacle ahead. Maybe it has a blinker on. And so then what we need to do is predict the trajectory for this obstacle. And so these are the points in time that the obstacle might take. So in this case, it can turn left, but it can also do a U-turn. Other things that we want to infer is give some notion of uncertainty to the planner of where could these points be. And then also at a maneuver level, what is the probability of each one to happen? Okay, so this is how we predict what we have to predict for trajectories. And then also depending on the development of the planner, we might also want to provide explicit intents for certain obstacles. So for instance, our car is driving there, there's 2 pedestrians, and maybe one of them actually intends to cross the road, cross the crosswalk. And we might just want very explicit semantic labels of like, this pedestrian is intending to cross the crosswalk with this probability. Or potentially a car is parked with this probability, so we might as well drive around it. And so that depends a little bit on how the planner is handling some of these situations. In this talk, I will focus more on the trajectory piece. So what the classical approaches and the deep learned approaches for those. Okay, so predicting traffic agents. So I said before, we want to predict the trajectories, uncertainties along each trajectory, and then a scoring or a probability for each type of trajectory. What sort of data can we use to predict this? So here we have a vehicle that is doing a lane change right in front of us. It actually has a blinker on. We can get some of the previous history data. We know its velocity. And there's other cars ahead. And we also know the lanes of the road, and it's possible to do a lane change here. So it's possibly likely that it will do that. So a little bit of more detail about everything we get from our stack. So perception can give us a lot of things. So unique IDs of each car, and as it tracks along time, position, heading, the dimensions of the car, car, bicyclists, pedestrians, velocities and accelerations, class labels, occlusion and visibility. This obstacle might be partially occluded by a certain percent. And certain attributes too, like stoplights, blinkers, door is open, is it an emergency vehicle? We also get static obstacles like road debris, traffic cones, construction zones, traffic light state, and then also a visibility map. So perception has LiDAR data. It knows there's actually certain parts of the space that we don't see. And so that can also be useful for prediction and for a planner too, for decision making. Like there's certain parts that are just really uncertain. And then another thing is the semantic map interface. So it gives us actually a lot of detail about already offline semantic information from the road. So we know these are all the lanes on the road, their geometries, and how they connect. So an example here in this lane here, it's a left turn only lane. It can turn onto this lane or onto this one. This one here, for instance, can only go straight. It also provides us information about like, okay, this traffic light is actually associated to specific lanes, and its state will allow like different behaviors in each of these different lanes. We also get yield information, stop information, crosswalk information. Okay. So next, a small overview of classical approaches. So this is going to get cluttered because people have tried a lot of different things. And so first things of classical approaches is, okay, we have all this map lane graph information. So the first thing we can do is really, okay, we can follow all these lanes and roll out all the possible hypotheses of lane following behaviors that an obstacle can do at different places in the map. So this obstacle here can turn right, can go straight. And then in terms of dynamics, lateral, longitudinal, sometimes are predicted independently, sometimes together. People have used simple vehicle models, use Kalman filters, but then also use driver models. This means you might have, for this obstacle here, you might have another car ahead with a different speed. That becomes another constraint in your problem. You have a stop, you know that likely the car will come to a stop at a stop line. People have also used a lot of data-driven parameter feeding to, for instance, estimate what are typical acceleration profiles for cars coming to a stop. And so these can be used in several of these models as well. And then also trajectory priors. So people use a lot of this driving data from the road, and just one option is you can cluster all these trajectory into prior trajectories. Okay. So then for trajectory uncertainty, some typical approaches is if you have a Kalman filter, you can propagate uncertainty through it. For instance, the perception stack can also give you covariances on the estimated velocity. And so that's something you can also provide as input to your Kalman filter. And then another thing is if you have clusters of trajectories, you can model them with, for instance, Gaussian models. And so if you fit those distributions to Gaussian distributions, then you can also get uncertainty from that. So covariances in that case. And then finally, for trajectory scoring, that's quite a few here. So very popular are heuristics. A lot of times it's like there is a blinker on, the car is coming towards this lane, lane change probability is very high. Or hand-engineered costs, so like a cost-based dynamical, sort of a dynamical function where it's like, okay, well, if the car is going to turn right here, but it's not decelerating, then the likelihood that it's turning right is pretty low, and you can add some of these costs up, and so that gives you also probability of scoring for different trajectory. Other stochastic approaches are, for instance, classifiers, just simple classifiers, and then if you have some probabilistic models, then just calculate the likelihood of the trajectory for each one of these. Yeah. Mm-hmm.
So
Yeah.
your example was there were two motions happening, left turn and then there's a U-turn.
Mm-hmm.
And say that there's a probability 36% to 1.
Yeah.
What does it come under? Is it like a scoring? Like one way to think of it is this a random process with sort of a mixture of two things happening.
Mm-hmm.
And with 36% time there's a left turn movement happening. So you could think of it as an uncertainty, or you could think of those scores as
mm-hmm.
How do you sort of differentiate between these two?
The idea is more like, okay, if this behavior is going to happen, and given like my models and the prior trajectories that always do a U-turn, this is kind of like, let's say, the covariance I see, the distributions I see. So for instance, you could have people doing left turns where some of them do a very tight cut and then other ones do more around it. So you could even just see, as you're doing the turn in the middle of it, maybe there is a pretty big distribution of the uncertainty of where a car could be. And so that's the uncertainty of you predicting the pose of the car at that point, right? Because based on the data, there's a lot. But then the other one is at a maneuver level. It's like, what's the probability that the car is doing a left turn versus the probability that it's doing a U-turn? Yeah. Yeah. So let me go back. Yeah. Yeah, so then here is where we start hitting a wall. Because thinking of engineering costs, lots of things that can affect the behavior of the different traffic agents. So let's see an example. See here, a bicyclist is actually starting to drive towards our lane because there's a parked obstacle right there. And so then here's interaction of them. But then you can also see some like corner cases where an obstacle, a truck actually is running a red light right in front of us. And so that's where it starts getting tricky because the behavior of an obstacle will depend on a lot of different factors. Crosswalks, are there pedestrians? Are there other obstacles ahead? Is there something that the other car is seeing that we aren't seeing? And so this really gets very complicated. And so when you're looking at modeling, trying to model a predicted trajectory or a probability based on some sort of a cost function, then you can blow out the list of things that you can consider. And just distance to the car ahead, or delta in velocity between cars, or is there a lane to the right or to the left? What are the distance to the lane edge? What are the changes in acceleration velocity? And so this is what we call, becomes a squishy ball problem, where it's like you might be tuning for certain cases for caring more about certain costs, and then for other cases less. And so then you're just like kind of stuck, and you can't get nowhere. And so this is where we start going more towards the deep models. So what people started considering is like, okay, can we kind of represent the world as a top view image where we can encode a lot of information? So first thing here is are the maps. So they are a little different, but you see the lanes of the road. They're turning right here. There are crosswalks. These green and the red, in this particular case, encode the traffic light state, so we can tell us people are actually allowed to drive on these lanes right now versus not. And so some of the first papers came from Uber. A little more detail, for instance, a different group at Uber they raster slightly different. You see the crosswalks here. They still connect their possible paths by these lines. They encode the heading in color. And then they put all the different obstacles on the road here. And then interestingly enough, they also encode the history of the obstacle. So like the previous 5 seconds or 4 seconds, the obstacle was here, 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 and here. And then they just get creative about like what sort of other information can we add to it. And so people at Zoox have done the same thing. They have a target agent they want to predict. It's here. They have other entities. They have a dynamic context, again, where they represent these lanes are green now. The traffic light is green. They can turn here. These lanes cannot do that. And then also represent the road network. One more example, Waymo, ChauffeurNet. They also represent the top view raster representation of the world. So it's a little harder to see, but red are the current and previous observations of the obstacles, and then green are the predicted trajectories. So you can see obstacles being predicted, okay, going straight, turning left. Some of them are gonna do a U-turn, and it sort of predicts that. I'll go back to this later, so, yeah. Field of view. Yeah, so this is where you can get a bit more creative too, which is, hey, you know that, there's cars that move here, and so like even you don't get LiDAR points if you get a big truck right in front of you. And so you could actually raster those two. I haven't seen yet a paper, but it's something where people would definitely be interested in experimenting that, especially things, a lot of times when you see pedestrians, they kind of get occluded by like either a tree or a traffic light, or there's a lot of people all together. And so that's where some representing that could be a good approach to try.
In these cases, it's as good as we're seeing the whole top view and predicting then what's going to happen.
Yeah. I'll get into more details too. So for instance, the first approach from Uber is, okay, we have the raster of the world. We have some CNN. One that worked well for them was the MobileNet V2. And then we can even have some vectorized features, in this case with state input, but you could add some other ones. And so you have the convolutional layer, and then you have like fully connected layers, not getting into the details of that, but then the output of it is, okay, the predicted trajectory. And your cost could just be, okay, let's minimize the L2 error across the entire trajectory. You can also leverage this even more. Okay, let's just model the output by some normal distribution in this case. And so then what you want to do is minimize the log likelihood of this output. Okay? And so you have some results here that are pretty interesting. These are from Uber. They even detect an obstacle doing a lane change. So one is ground truth blue, and the green is, well, I don't know which one is what, but ground truth and prediction. And then doing a right turn, let's see, like even here, cutting the turn a little bit, and then even some random obstacle coming from across and coming into this lane. And some uncertainty, you can even see, like usually for the right turn, you see a lot more uncertainty in the points in time. Okay, so going back to the chauffeur net, is a single hypothesis enough? If you look at this case, you actually will see the obstacle flickers between predicting a trajectory like this and this. Same thing, there will be a truck here that we see it's going to predict to turn right at the beginning, but then it goes there. And so it kind of flickers between the two. And so what they've noticed that happens is that, okay, when we are in an intersection like this is the obstacle we are predicting, the raster, and then this is the predicted trajectory. It does this. It's pretty much kind of an average of everything that had happened, which is most likely it's a go straight, a right turn, and a left turn, all clumped into one mode. So they started working on a multimodal prediction. But interestingly enough, with the mixture model, what will happen, and a lot of different papers have noticed that, is that if you just provide a mixture model, the predicted output, it kind of generates to one or two modes, and then all the other predicted trajectories are sort of degenerate. So they actually had to kind of force the network to make sure you create different predicted trajectories that are distinct enough. And so what they did is obviously, minimize the error between the closest predicted trajectory of the mode that is closest to the actual trajectory, but then also forced to maximize probability. And so this way, it really forces the different modes to show up. And so then as they did a small study, they increased the number of modes too. Now you see represented the right turn and going straight. And then here you see the third one. And then as they go more, it's interesting. They start seeing this behavior where it's a slow moving obstacle that will maybe just come to a stop or move very slowly there.
What exactly does that mean? Any group 4?
Say again?
Any group 4 versus any group 2? Big group 4, largest probability? What exactly?
Well, the question is, where do you want to use this data? So, if you want to use, right? Yeah. Yeah. So that's the hard question, which is, okay, when do you get enough? And when you have other types of intersections, how do you guarantee that you're going to have all the possible behaviors, and especially the ones that might have very low probability and rarely happen, but that might be safety critical? And so that's the part of when you want to bring this in the car, you want to be careful about bringing it to the car, because you might be missing a lot of behaviors that might be, even if low probability, you want the planner to decide whether to move with more caution to handle that probability. And then, okay, if it's really not going in front of me now, our own planner can decide to move.
So,
Yeah.
If I understood you,
Yeah.
the difference between the one and the four, you deciding to allow more behaviors, and then you put
Yeah, we are able to predict a lot more behaviors, more behaviors that the obstacles can take, so that then the planner can decide whether to take those into account or not, right? Because let's say the planner is here and wants to do some unprotected turn. It doesn't matter whether this obstacle is still going this way or just turning right. And getting something like this, it's not good. And then the other thing is you might go up to 4, but it's still going to average somewhere if there's like yet another mode that you're not modeling. So you really end up not having a guarantee that you have a trajectory that makes sense. Yeah, so this brings me to the limitations of the deep learned models. So one thing is we don't necessarily get a dynamic feasibility of the predicted trajectories. We don't guarantee that we get a prediction for all possible behaviors. So for instance, something that doesn't happen often on the road, tails, rare events, likely they will not show up in these models, but they could be safety critical. And this is a big deal when we want to bring this in the actual car. Another thing is interpretability and scene understanding for helping the decision-making block. So for instance, an obstacle might yield or might not yield, and we might want to tag certain hypotheses with, this is an hypothesis for the obstacle yielding, this is for not yielding, and these are probabilities for each. And they now planner decide what you want to do with it, but you get all this semantic information that goes along with the trajectories. The same thing, obstacle is parked. Is it? Okay, so it's okay to drive around, right? And then the other thing is data needs, which is, we'll go to the part of the data sets. Okay, so a couple of solutions. Yeah.
So far, if I understood it correctly, everything is interaction between the ego and one other obstacle.
Not necessarily, like other obstacles with other obstacles as well.
You take into account some obstacle is going to perturb another obstacle.
Exactly. Yeah, so that's the idea.
That kind of causal effect.
Yeah, so that's kind of the idea of the raster, which is like, this might not be the best example, but if there were another car here in front of the one we're predicting, or if there is traffic here, then you would expect that something like a predicted trajectory here, if there is a car here, then it's going to have to be shorter. Or if there's a pedestrian here, maybe it has to come to a stop for the pedestrian. And if there is traffic ahead, the same thing. Right. And so that is the advantage of the raster image, the top view image, is that you can at least encode a lot more information than just a feature of vectors. Yeah. Yeah. So in terms of dynamic feasibility, there's a couple of approaches where people, instead of just trying out predicting X and Y points and then doing some interpolation to get heading velocity accelerations, they instead predict directly acceleration and steering angle. And then they essentially just propagate that through like a simple bicycle model, for instance. And so then we guarantee that, so this is your prediction that translates into some predicted trajectory, and then you minimize the error based on this. So that's one interesting approach. They also tried not just like feasible inputs, acceleration and steering, but also lower order polynomial paths, predicted trajectories. And so just a little bit of intuition. When you have an unconstrained model, this might be hard to see here in the projector, but essentially this obstacle does this, turns kind of almost on itself, which doesn't make sense and in a non-holonomic model. And then this one is a lot more realistic, and you actually can have the bounding box go out of this lane a little bit more, which could be important for the planner. Another interesting thing about the number of modes, what people have also tried is, how about I already know the lane graph and I know all the following lanes for this obstacle, so why not just use it? So, you know, they just propose here in pink, okay, you please, for the network, generate a predicted trajectory that follows this lane, or generate a predicted trajectory that follows this lane. So you could guarantee that at least for how many possible lane sequences that you have, you are going to get a predicted trajectory. Another option, so another idea that Waymo was representing is, you can also have these anchor trajectories, which could be this, but could also be based on prior data. We clustered all this data, and so we have different options, and so this means the car can go straight, can turn left, or can come to just a slowdown. And so that kind of constrains it a little bit more. This is still not really enough. So expert systems normally can handle well simple and rare events. They need to be simple, can't be super interactive, but you do have a guarantee that of the output that you get. And so yeah, you get these guarantees of trajectory and what sort of hypotheses you are generating. And the plan, it's easier for the planner to interpret. Deep learned approaches can handle these complex environments better. And then in that squishy ball problem, I mean, they sort of automatically figure out what are the features that are important in certain cases. These don't show up. But so the idea is that, okay, simple places where we can bring these together a bit. So, well, maybe we can have the expert systems and then bring in the ML models to refine these predicted trajectories with state and uncertainty. So for instance, the anchor paths that I just showed. Also generate several expert trajectories or deep learned trajectories and calculate the probability. That could just be one place for it. And then another thing is just specific behaviors, maybe only for bicycles or maybe just for lane changes. And so we have a guarantee that we would always have an hypothesis for lane change hypothesis. But this is all pretty hard to integrate. One thing is, how do we detect online that one system might fail? It might not do very well in these cases, and maybe we have to use the other prediction system or model. Or, so when do we use one of each? And then the other thing is also, you can't use all these models for all obstacles, for all hypotheses, because we do have limited compute and time in the car. So then you have to be smart about, like, maybe what are the obstacles that we really care about predicting with a more complex model? What are other obstacles that we might just model with simpler models, but for completeness, they're there and they work fairly well. But yeah, how do you pick and choose each one of those? And this is like the biggest problem. And how can we bring this in the car? Yeah. So with this, I guess I still have some minutes for data set. So how do we create a data set? So ground truth for prediction, just a bit of intuition is, okay, we have a car driving on a road, time t0, t1, t2, t3. You can think of it seconds. And so then at time t0, we are going to generate a prediction t0 for this car. And the same at time t1, the car is there. So we'll generate another prediction. And the same for t2 and t3. And so we generate this prediction a few steps ahead in time. The same for t1, t2, t3. And then, okay, these are our predictions for a certain model. And then how do we measure the error? So, okay, we go look ahead for time t0. We go look ahead in time for the prediction for time t1. And we see what our error is. The same for t2, the same for t3. But then here we go, t4, we have no data because the car disappeared in our data set. So we actually can't really figure out, like, any of these ground truths. So we don't have that data. Okay, so that's one issue. Another thing is, but you know, that's how we measure. This is how well we're doing. We go in the future and look at the ground truth. Yeah. That's a good point. Yeah, you could. I think it might just not be enough information to then use it as a metric or a cost. But yeah. Yeah, and then this is actually interesting because it also biases a bit our data set to obstacles that drive along with our vehicle. We see them for a long time, so we always have like long time horizons. But then obstacles that turn onto a side road, we really only have that much prediction. It also means that we don't need to generate a prediction beyond that, but yeah. And then another thing that we can do is automatically and offline just tag certain intents. So an obstacle does a lane change here. It's kind of funny, the colors change, but we can just go mine in our data. Every time an obstacle kind of crosses to another lane, oh, that's our tag for a cut-in. And so then we can roll back in time and be like, okay, well, I give this scene, and now I can create a detector just from automatically detecting these tags on the road. Data sources. Well, so we can use perception in the future as our ground truth, because it has to be generated anyway. We can also use human annotations. Well, what are the trade-offs? This is pretty scalable because we're always going to be generating this in our missions in the car, and less costly. This is a lot more costly. The problem is you need to have a fairly mature perception system. So you need to be doing a lot of data cleanup and taking care of noise issues. So this one is better for correctness. Another advantage of perception, though, is that if you train your models on perception output, then you're also more robust to your perception noise. So when you deploy it in the car, at least you have a guarantee that you don't just start creating pretty bad trajectories because now suddenly your data is different. But then the thing you can use human annotations for is, first, you can pre-train your models on human annotation, but you can also do some sensitivity analysis. One thing that both would have issues with is what I mentioned, like limited and variable history horizon, but then also occlusions. And occlusions actually maybe mostly the perception, because if you have a long occlusion, perception will tend to suffer from, okay, this obstacle is not the same as the one before if it had a long occlusion. And so that means that even for us annotated data, this doesn't work as well. Humans would probably be better. Yeah. All right. Other thing is rare events. We have a lot of data, but not much data is interesting. It's really just a small amount. And the data is very imbalanced. So this is how much we see lane changes and other behaviors. This is how much data we have for intersections, or road means straight road. And then behaviors of cars going straight at an intersection or turning. And then what gets more complex is we are trying to predict behaviors and complex behaviors with complex interactions. So even just looking at these dimensions is probably not enough, because we have to balance our data, but then we have to take into account that there might be other behaviors that we need to make sure they're also balanced, and we don't know what the set of behaviors that we need is. So that is in itself another problem. Yeah, most vehicles follow lanes. Yeah, so, in terms of tooling, there's actually quite a bit of software engineering work on data samplers, scene detectors, interesting scenes, to get us a good training data and cleanup. We deploy models, and then we try to go find interesting cases. So can we detect rare events? Can we use these engagements as our other data? Can we find where our metrics really don't do well and make sure that gets added to our data set? And that's kind of like a vicious cycle of then we go and train more and get more of this data. And I think that's before. Yeah, so yeah, summary is more like, modeling complex interaction in various. So rasters are a promising approach, but they don't get all the guarantees that we need. So we need to be smart about how we integrate both. And then not all data is equal. And balancing the data set is hard, and figuring out what all driving scenarios that we are predicting is also hard. Another one that I didn't touch much on is also L2 error is not only metrics. There's also a lot of things to consider when we are deploying new models and how that affects our planner behavior. Because bear in mind, our planner is also not perfect, and it has a lot of heuristics. And so what we do in the prediction stack is also constrained by the architecture that we've decided to go with the planner. And so we just have to work together. And the same thing with perception. What we can do in prediction is dependent on what perception can provide us. Yeah. So finally, I just have the LIFT level 5 data set that was released at CVPR. So a little bit of the sensor configuration is we have the top LiDAR, 6 cameras, and then 1 long range camera in the front, and then 2 bumper LiDARs. And this data, actually, I think this is missing the Waymo data set that now has also been released. But it has 3D annotated frames, it has LiDAR data, camera data. It also has a drivable surface map, and we rasterize our semantic map with lanes and crosswalks. And this is how kind of it looks like. So you'll have data with some cameras, bounding boxes, LiDAR, and then this is kind of the raster view. And this is kind of our semantic map with the different lanes, the crosswalks represented. And I think I just have a video. We have, I believe, 25 second scenes of data, maybe 40. So yeah, we have all the 6 different cameras, and then this is, the raster of the semantic map with all the obstacles driving, and this is where our own ego is, and these are the LiDAR point clouds. Yeah. And I think that's it.
Anyone have any questions?
Do you model how the obstacle will behave as a function of the ego vehicle?
Not right now. It's a hard problem. And also making it in production. So the way we would want to do it is target to specific features that we want to deploy on the road, behavior, ability to handle certain scenarios. And so they would be specifically for things like lane change, where in tighter scenarios where you might actually want to, show your intent and see if the other car will actually behave like that, and also merge cases. Those will be the first places where we'll tackle that. We are not doing that at the moment. It's like a harder research problem, and we decided not to tackle it yet.
What exactly did you mean by intent? You said it someplace.
Intent. Yeah.
Mode choice or what?
So, for instance, we could predict that a car is going to do a lane change. Sometimes we call it a cut-in onto our road, our lane. We could predict the explicit trajectory, but we could also predict just a probability of the obstacle will cut in and we should behave to it. And so that would be much simpler if the planner has some logic that just handles that specifically. So depending on the planner needs, we could work on a path where we're just looking at, okay, a simple classifier for cut-in detection, and yeah, give it a probability to the planner.
That's what you mean by intent?
Intent, yeah. Or like a pedestrian intends to, a pedestrian might be on the sidewalk close to a crosswalk, and then does it intend to actually cross or not? Yeah.
So I have two questions. One is about, so suppose we take the example that you mentioned like early on, which was the turn, the left turn, and then this U-turn. And let's say that the probabilities you actually get when you're close to that obstacle is like 0.6 and 0.4. Now, I'm wondering how you think about decision making based on this prediction output. Do we look at it as, are you supposed to be robust to both outcomes? In this case, it seems to be the case, right? But what if it's 0.9 and 0.1? Or what if it's 0.99 and 0.01? What is the threshold? Or is there a threshold beyond which you are certain that? And how to think about that threshold? Yeah.
I would say that depends on maturity of your planner. You could be very simple and just decide, I'm gonna throw away everything that is below 0.2 and just have a threshold, and then everything else is a constraint for me. So, you know, if there are other paths with high likelihood, they will be constraints, and it will be, or you can take all of them into account and be super careful. Or then you can go under probabilistic decision making, and then they would take all of these constraints into account.
So in practice, what is kind of the way things are done?
Ideally, the latter, but it depends how far along you've gone, right? So.
If I may, I have another question about sort of prediction from data. So here the idea is that you look at a lot of examples and then sort of learn to predict what's going to happen. I'm wondering if there are events, so accidents are themselves very rare events. Are there, if there are events that are very rare, rarely happen, certain sort of complex interactions, what is the way of thinking about whether you have coverage of all examples possible or enough examples such that our predictions are, is there some notion of, like how do we think about these things?
Oh, we don't know. Yeah, we don't know. Are there enough examples? Do we create just an expert model for that? Because we would know that data-driven models would not pick that rare event. Another option is you could use simulation to try to, based on those cases that you can mine from data, maybe like add some perturbation and like create a few more cases. That's a bit more synthetic. You might have some biases, but yeah, it's not an easy problem. Yeah.
Okay, let's thank the speaker. Thank you, Anna.
All right.